Right now, a wound in the sun's atmosphere is rotating to face Earth, and it's not stopping to ask permission. A transequatorial coronal hole, bleeding high-speed solar wind at 700 kilometers per second, will arrive this weekend. California's faults haven't moved in over a century. An oarfish, the so-called doomsday fish, surfaced in Monterey Bay 3 days ago. Electromagnetic monitoring stations detected 37 hertz anomalies before going mysteriously dark. And our magnetic shield, Earth's primary defense against solar fury, is thinning in ways that make scientists uncomfortable. Are these unrelated coincidences? Or are we watching multiple Earth systems converge toward a threshold nobody wants to cross? Subscribe and follow along, because what we're witnessing might not be advance notice at all. It might be the opening act of an event the planet has been orchestrating in silence for decades. Right now, as you're reading this, a gaping wound in the sun's atmosphere is rotating into position. It's not a solar flare. It's not a coronal mass ejection. It's something more patient, more relentless. A transequatorial coronal hole, stretching across both hemispheres of our star, is beginning to face Earth directly. And unlike the violent bursts we're used to tracking, this one doesn't explode and fade. It bleeds. Coronal holes are regions where the sun's magnetic field opens up and allows solar wind to escape at extraordinary speeds. Think of the sun as having a skin, a corona, that normally holds its atmosphere close. But in these holes, that skin tears open, and superheated plasma rushes out into space at speeds exceeding 700 kilometers per second. When a flare hits Earth, it's like getting punched. When a coronal hole faces you, it's like standing in a river current that doesn't stop pushing for days. This particular hole carries negative polarity, solar wind. Polarity matters because Earth's magnetosphere, our planetary magnetic shield, responds differently depending on whether incoming solar particles carry a north or south magnetic orientation. Negative polarity, what scientists call southward-pointing interplanetary magnetic field, couples more efficiently with Earth's own magnetic field. It's like two magnets being forced together in the wrong orientation. They don't repel cleanly. They twist, they compress, they create turbulence at the boundary. The duration is what separates this from typical space weather events. A coronal mass ejection might buffet Earth's magnetosphere for 12 to 24 hours before dissipating. A high-speed solar wind stream from a coronal hole can maintain pressure for 3 to 5 days straight. It arrives on January 9th or 10th, 2025, and it doesn't let go quickly. Our magnetic field will be compressed continuously, pushed inward toward the planet's surface, squeezed like a stress ball held in a fist that won't release. Imagine Earth's magnetosphere as a shock absorber surrounding the planet. Under normal conditions, it extends tens of thousands of kilometers into space on the sun-facing side, creating a protective bubble. When high-speed solar wind arrives, that bubble gets crushed. The dayside magnetosphere can compress by 30 to 40%, bringing the boundary much closer to where satellites orbit, where our atmosphere begins to thin, where the interface between space and Earth becomes uncomfortably narrow. The forecasted geomagnetic storm levels are only gone to G2, minor to moderate, on the official scale. Scientists aren't predicting a Carrington event. Power grids won't collapse. GPS won't fail catastrophically. This isn't the kind of space weather that makes emergency broadcasts, but intensity alone misses the point. What matters isn't how hard you hit a system. What matters is whether that system was already near its breaking point. Metastability is a concept from physics that describes systems appearing stable until a tiny nudge causes sudden, irreversible change. A boulder balanced on a ridge looks motionless for centuries. Then a pebble rolls against it, and the boulder falls. The pebble didn't cause the instability. It simply arrived when conditions were perfect for transition. Earth's tectonic systems, its magnetic field asymmetries, its atmospheric electric properties, all exist in states of metastability. They hold tension. They wait. Let's be absolutely clear about something before we go further. Mainstream seismology does not support a causal link between solar wind and earthquakes. The energy transfer mechanisms are poorly understood, the statistical correlations are weak, and prediction based on space weather remains firmly in the realm of speculation. But timing is not causation, and yet timing can still matter. If a fault system is late in its seismic cycle, already loaded with accumulated stress, already near the threshold of rupture, then even small perturbations, Even changes that wouldn't matter in other contexts might matter now. We are watching a convergence. The solar activity cycle is near its maximum. Coronal holes become larger and more frequent as the sun's magnetic field reorganizes. Earth's own magnetic field is in a period of rapid change, weakening in some regions, shifting in orientation. The Pacific tectonic system, from Alaska through California to Mexico, is in a documented stress accumulation phase. And now, in early January 2025, these cycles are overlapping, not colliding, not causing each other, simply arriving at the same moment in time. There are other signals appearing in the noise. Electromagnetic anomalies detected in the Schumann resonance cavity. Marine life behaving in ways that folklore has long associated with tectonic unrest. An interstellar object that passed through the solar system in late 2024, leaving researchers uncertain about plasma interactions. None of these alone constitute evidence, but patterns emerge when systems approach thresholds. Weak signals that would normally be ignored start appearing together, clustering around the same temporal window. The high-speed solar wind stream is expected to arrive this weekend. It will compress Earth's magnetosphere. It will alter ionospheric current systems. It will create conditions that haven't occurred in this particular combination for years, possibly decades. Whether that matters depends entirely on what it's pressing against. So the question isn't really about the solar wind itself. The question is about readiness, about accumulated stress, about whether multiple Earth systems, already near their limits, will respond to a push that arrives at exactly the wrong time. If this pressure arrives now, what exactly is it pressing against? The Pacific Ring of Fire has been rearranging itself for the past 5 years, in a pattern that seismologists recognize but don't particularly like discussing publicly. From Alaska to Mexico, the subduction zones and transform faults that define the western edge of North America have been rupturing in sequence, north to south, releasing centuries of accumulated strain. Except for one section, California has remained silent. And in seismology, silence is not peace. In 2018, a magnitude 7.1 earthquake struck Anchorage, Alaska, causing significant infrastructure damage and reminding the Pacific Northwest that the northern segments remain active. In 2021, a magnitude 8.2 event ruptured off the Alaska Peninsula, one of the largest earthquakes globally that year. Moving south, the Cascadia subduction zone experienced increased slow slip event frequency and tremor activity, suggesting stress migration along the fault interface. Then, in 2023, the Sierra Madre Occidental region of Mexico experienced a magnitude 7.6 earthquake, followed by a magnitude 7.1 aftershock. The southern bookend had released. The northern bookend had released. California, the middle segment, has not. A seismic gap is not a lack of seismic activity. It's a stress deficit, a section of fault that should have ruptured based on historical patterns and strain accumulation rates, but hasn't. The longer a gap persists while surrounding areas release stress, the more loaded that segment becomes. It's the tectonic equivalent of a dam holding back water while tributaries on both sides overflow. Eventually, the dam either releases gradually through controlled mechanisms or it fails. California's major fault systems, the San Andreas, Hayward, and Calaveras faults in particular, are capable of producing magnitude 7 to 8 earthquakes. The last major rupture on the southern San Andreas occurred in 1708. The last significant event on the northern segment was the 1906 San Francisco earthquake. That's 119 years of silence on the northern section and over 300 years on the southern section. Meanwhile, GPS monitoring shows that strain continues accumulating. The Pacific Plate continues moving northwest relative to the North American Plate at roughly 5 centimeters per year. That motion doesn't stop. It either gets accommodated through continuous creep or stored as elastic strain to be released catastrophically. The concerning aspect isn't that California is due for an earthquake based on some average recurrence interval. Earthquakes don't follow schedules. The concerning aspect is that late-cycle fault systems become increasingly sensitive to small perturbations. When a fault is early in its loading cycle, it can absorb external stresses without triggering rupture. When a fault is late in its cycle, already near the threshold of static friction failure, even minor changes in stress conditions can initiate rupture. It's the difference between pushing a car that's in neutral versus pushing a car that's already rolling. The energy required to cause motion drops dramatically. This sensitivity extends to stress changes that aren't directly horizontal along the fault plane. Vertical stress modulation, changes in crustal loading from atmospheric pressure, ocean tidal forces, or even changes in the planet's magnetic field that induce telluric currents, can all slightly alter the stress state on a fault. The Bay Area fault system is particularly sensitive to these vertical components because the faults there are not purely strike-slip. They have significant dip angles, meaning vertical forces can translate into shear stress changes on the fault plane. There's a hypothesis in seismology that remains controversial but refuses to die, the antipodal earthquake correlation. The idea is that large earthquakes on one side of the planet can induce stress changes on the opposite side through body wave propagation and mantle resonance. When a magnitude 8 earthquake occurs, seismic waves travel through the entire Earth. At the antipodal point, waves arriving from all directions converge and focus, creating a stress concentration. Most of the time, this doesn't matter. But if the antipodal location happens to be on a late-cycle fault system, the additional stress might be sufficient to tip the balance. The December 23, 2024 earthquake in Vanuatu, a magnitude 7.3 event, occurred at a location roughly antipodal to the California coast. The exact antipodal point of the Vanuatu earthquake falls in the Pacific Ocean west of Los Angeles, approximately 300 kilometers offshore. It's not a perfect alignment, but stress focusing doesn't require precision. Waves converge in a broad zone around the antipodal point. Whether this caused any measurable stress change in California's fault systems remains unknown because we don't have instruments sensitive enough to detect such subtle shifts buried in background seismic noise. What we do know is that the pattern of seismic activity surrounding California suggests stress migration is occurring. Small earthquakes along the San Andreas have increased in frequency near Parkfield, the section of the fault that typically ruptures every 22 years and last broke in 2004. Swarm activity has been detected near the Salton Sea, the southern terminus of the San Andreas, where it connects to the Imperial Fault. These are not necessarily precursors, but they indicate that stress is moving through the system, probing for weak points, testing the locks that have held for decades or centuries. The public conversation about California seismicity often centers on fear of the big one, a hypothetical magnitude 8+ earthquake that ruptures multiple fault segments simultaneously. That framing, while dramatic, misses the actual risk profile. The big one might never happen as a single event. What's more likely is a cascade, a sequence of large earthquakes triggering each other across different fault segments over weeks or months. The danger isn't a single rupture. The danger is synchronization, multiple systems failing in rapid succession because stress conditions have aligned. And now, while California's faults remain locked and loaded, while stress indicators show increasing activity on surrounding segments, while the tectonic system sits in a documented late-cycle phase, space weather is about to deliver sustained pressure to Earth's magnetic field. The question isn't whether solar wind causes earthquakes. The question is whether a compressed magnetosphere, altering electric currents in the crust, changing atmospheric loading patterns, subtly modifying stress conditions at fault interfaces, arrives at a moment when those changes matter. If the ground is already tight, what happens when the planet's shield flexes unevenly? We need to talk about Earth's magnetic field without invoking apocalypse. The narrative you've probably heard is that our magnetic shield is collapsing, weakening towards zero, leaving Earth vulnerable to solar radiation that will strip away the atmosphere and sterilize the planet. That's not happening. What is happening is more subtle, more asymmetric, and potentially more concerning for near-term Earth systems than a simple global decline. Earth's magnetic field is not failing, it's reorganizing. Over the past 2 centuries, the field strength has decreased by approximately 9% globally. That sounds alarming until you learn that magnetic field strength varies naturally over millennial timescales, and current levels remain well within historical norms. The magnetic poles are moving, yes, accelerating their drift rates, but pole reversals occur every few 100,000 years, and the process takes thousands of years to complete. We're not in immediate danger of losing magnetic protection, but we are experiencing something unusual, localized thinning and asymmetric weakening that creates vulnerabilities in specific regions. The South Atlantic anomaly is the poster child for this asymmetry. Over the South Atlantic Ocean, between South America and Southern Africa, Earth's magnetic field strength is roughly 30% weaker than the global average. This creates a region where the inner Van Allen radiation belt dips closer to Earth's surface, exposing satellites and aircraft to higher radiation levels. The anomaly is growing, expanding westward, and splitting into two lobes. Scientists track it closely because it affects spacecraft operations, astronaut safety, and potentially atmospheric chemistry in the region. But field asymmetry isn't limited to the South Atlantic. The entire magnetosphere exhibits north-south asymmetries and day-night variations. During periods of high-speed solar wind, the day-side magnetosphere compresses, while the night side stretches into a long tail. This compression isn't uniform. The magnetopause boundary, where Earth's magnetic field meets the solar wind, experiences localized thinning where field lines reconnect. At these reconnection points, solar particles can penetrate deeper into the magnetosphere, accessing regions normally shielded. When a coronal hole delivers sustained high-speed solar wind, the magnetosphere doesn't just shrink uniformly, it wobbles. It develops pressure gradients. Field lines on the day side get pushed earthward, while night side field lines stretch and sometimes snap, releasing energy in substorms. These dynamic processes create temporary weak points that migrate around the planet. For most purposes, this doesn't matter. Satellites adjust orbits. Power grid operators monitor for induced currents. Life continues. But Earth's systems are coupled. The magnetosphere connects to the ionosphere through field-aligned currents. The ionosphere connects to the atmosphere through chemical and electrical processes. The atmosphere connects to the crust through pressure loading and atmospheric tides. And the crust, particularly in tectonically active regions, responds to changes in electrical currents flowing through conductive rock layers. These are called telluric currents, natural electrical currents induced by variations in Earth's magnetic field. Telluric currents flow through the crust continuously, driven by the same magnetic field variations that create auroras. Their strength depends on the conductivity of crustal rocks, which varies dramatically based on composition, temperature, and fluid content. Fault zones, because they're fractured and often contain fluids, are more conductive than surrounding rock. This means telluric currents preferentially flow along faults. During geomagnetic storms, even minor ones, telluric current density increases. The currents grow stronger, penetrate deeper, and can alter the electrical and mechanical properties of fault zone materials. Here's where certainty ends and speculation begins. We know telluric currents exist. We know they vary with magnetic activity. We know fault zones are conductive. What we don't know with confidence is whether changes in telluric current density can alter fault friction or pore pressure enough to influence rupture timing. The energy involved seems too small. A typical geomagnetic storm induces currents measured in amperes per kilometer of fault length. Compared to the tectonic stresses measured in millions of pascals, this seems negligible. But metastable systems don't respond to absolute force magnitudes. They respond to gradient changes, to alterations in boundary conditions, to perturbations that occur when the system is already balanced on the edge of transition. If a fault is locked by static friction and already loaded to 99% of failure stress, then a 1% change introduced by altered electrical conditions, by pore pressure modifications, from current-induced heating, by any mechanism that slightly reduces the effective coefficient of friction, could be sufficient. The ionosphere itself is experiencing asymmetry during this solar wind event. Northern and southern hemisphere ionospheric current systems don't mirror each other perfectly during geomagnetic disturbances. Seasonal differences, magnetic field geometry, and local time all create hemispheric imbalances. When one hemisphere's ionosphere heats and expands, while the other remains relatively stable, pressure coupling to the neutral atmosphere becomes uneven. This drives atmospheric circulation patterns that can alter surface pressure distributions on timescales of days. Surface pressure changes of even a few millibars translate to stress changes of hundreds of pascals on crustal faults. Again, this seems small compared to tectonic forces. But California's fault systems are not isolated. They're part of a coupled Earth system where atmospheric loading, ocean tides, groundwater changes, and yes, magnetic field variations all contribute to the total stress state. Remove any single factor, and rupture probably doesn't occur. But combine them all during a period of peak tectonic loading, and the probability shifts. The magnetosphere isn't failing. It's responding to solar forcing in ways that create temporary, asymmetric weak points. Those weak points alter electromagnetic environments at Earth's surface. Those alterations drive currents through conductive crust. Those currents flow along fault zones. And those fault zones, in California specifically, are late in their seismic cycles. The chain of causation is uncertain at every link, but the chain exists. The shield isn't failing, it's flexing unevenly, and Earth systems don't like imbalance. If the magnetic system is shifting, where would we see the signal first? The space between Earth's surface and the ionosphere forms a cavity, roughly 100 kilometers tall, wrapped around the entire planet. This cavity resonates at specific frequencies determined by its dimensions and the speed of electromagnetic waves. Lightning strikes excite these resonances continuously, creating a global electromagnetic background hum that has existed since Earth developed an atmosphere. We call these Schumann resonances, named after the physicist who predicted them in 1952. The fundamental mode resonates at approximately 7.83 hertz. Higher harmonics occur at roughly 14, 20, 26, 33, 39, and 45 hertz. For decades, Schumann resonances were considered stable, varying slightly with seasonal changes in global thunderstorm activity but otherwise predictable. Then monitoring improved. Researchers began noticing that during geomagnetic storms, ionospheric disturbances, and periods of unusual tectonic activity, the resonance frequencies and amplitudes could shift dramatically. The cavity properties change when the ionosphere's electrical properties change. And the ionosphere's properties change constantly in response to solar radiation, particle precipitation, and atmospheric dynamics. What's drawing attention now isn't the fundamental 7.83 hertz mode, it's activity in the 32 to 37 hertz range. This falls between the 5th and 6th harmonic modes, a region where amplitude should be relatively low under normal conditions. Yet multiple monitoring stations have reported high amplitude spikes in this frequency range during the first week of January 2025, coinciding with increased solar wind speed and the approach of the coronal hole stream. Explaining why 37 Hz matters requires understanding that Schumann resonances aren't just passive electromagnetic echoes. They're active components of the global electric circuit. Lightning drives current upward into the ionosphere. That current flows horizontally through the conductive ionosphere, then returns to Earth's surface through fair weather regions. This circuit couples atmospheric electricity to crustal conductivity. When resonance patterns shift, circuit properties change. Current distributions alter, and in regions with conductive fault zones, those altered currents preferentially flow through tectonically active areas. Several factors can drive anomalous activity in the 30 to 40 Hz range. Ionospheric heating from geomagnetic storms changes cavity dimensions effectively, raising resonance frequencies. Localized ionospheric disturbances, called traveling ionospheric disturbances, can create temporary resonance modes that don't match global patterns. Unusual lightning activity, particularly Sprite discharges high in the atmosphere, can excite higher harmonics more strongly than typical cloud-to-ground lightning. And some researchers, controversial ones, suggest that pre-earthquake stress release in the form of radon emission and electromagnetic effects might modulate ionospheric conductivity above tectonically active zones. The 37 Hz signal appeared on January 3, 2025, spiked again on January 5th, and then monitoring data from several stations went offline. For approximately 60 hours, from January 6th through early January 8th, publicly accessible Schumann resonance data from key monitoring locations became unavailable. Equipment failures happen, data transmission issues occur, but the timing, during a period of elevated solar wind speed, increased geomagnetic activity, and documented frequency anomalies, raises questions that monitoring gaps make impossible to answer. Let's be clear about what we're not claiming. Schumann resonance anomalies are not earthquake predictors. The scientific literature contains numerous papers exploring possible pre-seismic electromagnetic signals, and the results are inconsistent at best. For every study showing correlation between electromagnetic anomalies and subsequent earthquakes, another study finds no correlation. The signal-to-noise ratio is terrible. Electromagnetic disturbances occur constantly from solar, atmospheric, and human-generated sources. Identifying which signals, if any, relate to tectonic processes requires statistical rigor that most studies lack. The problem is that meaningful signals only become identifiable after the event they supposedly preceded. You can't know whether a Schumann resonance spike on January 5th indicates tectonic stress or just unusual thunderstorm activity until you see what happens in the following week. This makes prediction impossible and pattern recognition unreliable. We're left with suggestive correlations that could be coincidence, confirmation bias, or genuine physical coupling that we don't yet understand. What we can say with confidence is that electromagnetic anomalies and seismic activity sometimes cluster temporally. The Loma Prieta earthquake in 1989 was preceded by reports of unusual electromagnetic noise. The Northridge earthquake in 1994 occurred during a period of documented ionospheric disturbances. The 2011 Tohoku earthquake was preceded by ionospheric electron density anomalies detected by satellites. None of these were predicted. All were identified retrospectively. But the pattern of co-occurrence persists across different earthquake types, different monitoring systems, and different geographic regions. The 37 hertz activity, the data blackout, the timing relative to incoming solar wind, none of this proves tectonic coupling. But it adds another data point to a growing list of anomalies appearing during the same temporal window as elevated seismic risk. Electromagnetic systems, magnetic field perturbations, ionospheric instabilities, and crustal stress might be genuinely coupled in ways our current models don't capture. Or they might be independent systems that occasionally align by chance, creating the illusion of connection. Either way, the question remains open. Instruments that should be monitoring electromagnetic precursors went dark during a critical period. When they come back online, if they come back online before significant seismic activity, we'll have data to analyze. If they return after an event, we'll have correlation without causation once again. A pattern we recognize but cannot predict, a signal we see only when it's too late to matter. If instruments struggle, could biology be sensing something we can't yet model? On January 4th, 2025, snorkelers in Monterey Bay encountered a creature that had no business being near the surface. An oarfish, roughly 4 meters long, its ribbon-like body shimmering silver and undulating through shallow water where humans could reach out and touch it. Oarfish are deep-sea animals, typically inhabiting depths between 200 and 1,000 meters, feeding on zooplankton and small fish in the mesopelagic zone where sunlight doesn't penetrate. They surface only when something is deeply wrong. The encounter lasted perhaps 15 minutes before the oarfish descended back into darker water. Witnesses described it as moving with an otherworldly grace, its elongated body rippling in vertical waves, its crimson dorsal fin running the entire length of its spine like a mane of fire. Some reached out to touch it, their hands meeting cool, slick flesh that felt somehow wrong in the warm surface waters. The oarfish tolerated the contact briefly, then simply dropped away, disappearing into the blue-green darkness below as suddenly as it had appeared. The oarfish sighting went viral immediately. Not because oarfish are particularly rare, they're found in oceans worldwide, but because of what they supposedly represent. In Japanese folklore, oarfish are called Ryugu no Tsukai, messengers from the sea god's palace. They appear before earthquakes and tsunamis, rising from the depths to warn coastal communities of impending disaster. After the 2011 Tohoku earthquake, Japan experienced a cluster of oarfish strandings in the months before the magnitude 9.1 event. 20 oarfish washed ashore, or were spotted near the surface, between late 2010 and March 2011. The pattern was noticed. The earthquake happened anyway. Folklore often encodes observations that predate scientific explanation. Fishermen and coastal communities have documented oarfish appearances before seismic events for centuries. Dismissing this as superstition ignores the possibility that deep-sea organisms might detect environmental changes invisible to surface-dwelling humans and their instruments. The question isn't whether oarfish predict earthquakes. The question is whether they react to the same precursory signals that scientists have been trying to measure instrumentally. Understanding why an oarfish surfaces requires understanding where it normally lives. The mesopelagic zone, sometimes called the twilight zone, exists between 200 and 1,000 meters depth. No sunlight penetrates. Pressure increases dramatically, reaching 100 atmospheres at 1,000 meters. Temperature drops to near freezing. Food is scarce, consisting mainly of marine snow, organic debris drifting down from surface waters. Everything about this environment is extreme by surface standards, yet oarfish are perfectly adapted to it. Oarfish live in an environment dominated by pressure, darkness, and electromagnetic fields. At depth, they navigate using lateral line systems that detect water pressure changes, electroreceptors that sense weak electric fields, and possibly magnetoreceptors that allow them to orient relative to Earth's magnetic field. These sensory systems evolved to detect prey, avoid predators, and navigate in total darkness. But they also make deep-sea fish exquisitely sensitive to environmental perturbations that surface animals and humans cannot perceive. Their lateral line system is essentially a distributed pressure sensor running along both sides of their body. It detects minute pressure variations caused by water movement, allowing the fish to sense currents, obstacles, and other organisms without seeing them. In the stable environment of the deep sea, this system operates with extraordinary sensitivity. A pressure change of a fraction of a pascal, completely undetectable by human instruments at those depths, might register clearly to an oarfish. The electroreceptor system is equally remarkable. All living organisms generate weak electric fields through cellular metabolism and neural activity. Predatory fish use electroreceptors to detect these fields, essentially sensing the bioelectric signatures of prey hidden in darkness or buried in sediment. But electroreceptors don't distinguish between biological and geological sources of electric fields. If the ocean floor begins generating anomalous electric potentials, an oarfish would detect them. One hypothesis, speculative but grounded in known physics, is that pre-seismic stress changes in ocean floor crust create localized electric fields in seawater. As rock compresses before an earthquake, piezoelectric effects in quartz-bearing minerals generate weak electric potentials. These potentials drive currents through pore fluids in the crust, which then leak into seawater near the ocean floor. The resulting electric field anomalies would be strongest near fault zones and detectable by organisms with electroreceptors. The piezoelectric effect is well documented. Quartz crystals, subjected to mechanical stress, develop electric charge separation across their structure. Laboratory experiments demonstrate this clearly. The question is whether pre-seismic stress, the gradual compression of rock leading up to fault rupture, generates sufficient piezoelectric potential to create detectable fields in seawater. Calculations suggest the fields would be weak, measured in microvolts per meter. But weak doesn't mean imperceptible to organisms whose sensory systems evolved to detect exactly these kinds of signals. Another possibility involves pressure changes. If fault compression alters pore fluid pressure in submarine crust, that pressure change could propagate through overlying sediments and into the water column. Deep-sea organisms, living near the ocean floor, might sense these subtle pressure gradients. A change of a few pascals wouldn't affect surface measurements, but could be significant for animals whose entire sensory world is calibrated to detect pressure variations. The mechanics of how crustal stress might alter ocean floor pressure deserve examination. Submarine faults aren't simply cracks in rock. They're complex zones, filled with fractured material, fluids, and sediments. When tectonic stress compresses these zones, pore fluids can't escape instantly. Pressure builds in the pore spaces, a phenomenon called dilatancy. This pressurized fluid can migrate through the fault zone and potentially into overlying sediments and seawater. The migration creates pressure gradients that propagate outward from the fault. Magnetic field disturbances represent a third potential mechanism. If tectonic stress alters rock magnetization, or if piezoelectric currents generate secondary magnetic fields, organisms using magnetoreception for navigation might experience disorientation. Oarfish rising to the surface could be attempting to escape confusing magnetic signals at depth, or they could be following electromagnetic gradients that normally guide them horizontally, but during anomalous conditions point upward. Magnetoreception in fish remains poorly understood compared to electroreception. Some species definitely possess it, using it for long-distance navigation during migration. Whether oarfish use magnetoreception is unknown. They're too difficult to study in their natural habitat. But if they do, and if submarine tectonic activity generates magnetic anomalies, the fish might experience what amounts to navigational confusion. The magnetic landscape they rely on for orientation suddenly contains features that shouldn't exist, gradients pointing in wrong directions, field strengths that don't match their internal map. The challenge with all these hypotheses is verification. We can't instrument the ocean floor densely enough to detect electric field or pressure anomalies before earthquakes reliably. We can't monitor oarfish behavior continuously because they're difficult to observe at depth. We're left with after-the-fact correlations, anecdotes about fish behaving strangely before major earthquakes, strandings that cluster temporally near seismic events, and folklore that spans cultures and centuries but lacks mechanistic explanation. Chinese historical records document unusual fish behavior before earthquakes dating back over 2,000 years. Mediterranean cultures have similar traditions. Pacific island communities incorporate fish behavior into their disaster preparedness frameworks. The consistency across cultures and time periods suggests the observations are real, even if the interpretation varies. Modern science tends to dismiss anecdotal evidence, requiring reproducible experimental results. But earthquake precursors are, by definition, not reproducible on demand. We can only observe what nature provides. What makes the Monterey Bay sighting noteworthy isn't the oarfish itself. It's the timing. January 4th, 5 days before the expected arrival of high-speed solar wind, during a period of documented Schumann resonance anomalies, while California's seismic gap remains locked and loaded. The oarfish appeared in one of the most seismically active coastal regions in North America, directly above the Monterey Bay fault system, in waters overlying the transition zone between the Pacific and North American plates. The Monterey Bay region is geologically complex. The San Andreas Fault runs onshore approximately 100 kilometers to the east. The Monterey Bay Fault Zone, a smaller but active system, runs directly beneath the bay itself. The continental shelf in this region is unusually steep, with the ocean floor dropping rapidly from shallow coastal waters to depths exceeding 1,000 meters within a few kilometers. This bathymetric complexity creates oceanographic conditions different from most coastal areas: strong currents, upwelling zones, and unusually productive waters that support diverse marine life. If pre-seismic signals are being generated by stress accumulation on nearby fault systems, Monterey Bay represents an ideal location for those signals to affect marine life. The proximity to multiple fault zones, the steep bathymetry, allowing deep water organisms easy access to the surface, and the productive waters supporting populations of creatures like oarfish all combine to make sightings more likely here than in other seismically active coastal regions. Biology may function as a reactive sensor rather than a predictive tool. Animals don't forecast earthquakes. They respond to environmental changes that humans measure poorly or ignore entirely. When multiple species exhibit unusual behavior simultaneously, when deep-sea fish surface, when birds alter migration patterns, when terrestrial animals display restlessness, the convergence might indicate that environmental conditions across multiple domains, electromagnetic, pressure, chemical, are shifting in ways that biological systems detect immediately and technological systems capture only in retrospect. Japanese researchers attempting to use oarfish sightings for earthquake prediction have found that roughly 30% of strandings occur within 1 month of a significant seismic event in the region. That's a terrible prediction success rate, but it's also statistically significant. Oarfish strandings are rare enough that random chance wouldn't produce 30% correlation. Something is happening. We just don't know what. The 30% figure comes from analyzing decades of records, correlating documented oarfish appearances with earthquake catalogs. The correlation isn't perfect. Some strandings occur with no subsequent seismic activity. Some major earthquakes occur with no preceding oarfish sightings. But the statistical relationship persists even when controlling for reporting bias and confounding variables. It's not strong enough for prediction, but it's too strong to dismiss as coincidence. The Monterey oarfish is swimming back into deep water now. If it survived the surface encounter, it won't file a report. It won't tell us what it sensed. But it came up for a reason, driven by stimuli its evolutionary history taught it to avoid. Whether that reason connects to tectonic stress, electromagnetic disturbances, or something else entirely, we won't know until either the environment stabilizes or something significant happens. If Earth, oceans, and sky are all showing stress, what else has been moving through the system? In late November 2024, an object designated C/2024-S1, also known as 3I Atlas, made its closest approach to the Sun and began its journey back into interstellar space. Unlike the vast majority of comets that orbit our sun in elliptical paths, returning periodically over decades or centuries, 3I Atlas is a hyperbolic visitor. It came from outside our solar system, passed through once, and is now leaving forever, its trajectory bent by the sun's gravity but not captured by it. This makes it only the third confirmed interstellar object detected passing through our solar system, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The scientific consensus on interstellar objects is straightforward. They're probably fragments of planetary systems disrupted during formation, icy bodies or rocky debris ejected by gravitational interactions with giant planets in other star systems. They travel through interstellar space for millions of years before occasionally passing through another star's influence. Our solar system, traveling through the Milky Way, encounters these objects randomly based on galactic density and relative velocity. There's nothing mysterious about their existence. They're expected, predictable, and most pass unnoticed because they're small and dim. 3I Atlas fit this profile initially. Astronomers detected it using the Atlas Survey System, the same network that tracks near-Earth asteroids for impact risk. Early observations suggested a typical comet composition, water ice, and organic compounds, outgassing as it approached the sun and creating a faint tail. Its trajectory indicated an origin from outside the solar system, with an incoming velocity that couldn't be explained by solar orbital mechanics. It swung past the sun, surviving perihelion, and began accelerating back toward interstellar space. By mid-December 2024, it had passed Mars' orbit outbound. By early January 2025, it cleared Earth's orbit distance on its way out. What drew attention wasn't the object itself, but its timing and properties. 3I Atlas passed through the solar system during solar maximum, the peak of the sun's 11-year activity cycle, when coronal holes are frequent, solar wind speed is elevated, and space weather is generally more dynamic. Interstellar objects carry their own magnetic fields embedded in surface ices and potentially in their internal structure. When these fields interact with the sun's magnetic field and the surrounding heliosphere, they can create localized perturbations. Some researchers, operating at the speculative edge of space physics, have proposed that large interstellar objects might disturb the ambient plasma environment as they pass through. The heliosphere is filled with solar wind plasma, magnetized and flowing outward. An object several kilometers in size, moving through this plasma at hyperbolic velocity, could create a bow shock, a wake, and potentially excite instabilities in the local magnetic field structure. These effects would be subtle, detectable only with sensitive plasma instruments on spacecraft, and unlikely to influence planets millions of kilometers away. But unlikely isn't impossible. If an interstellar object happened to pass through the heliosphere during solar maximum, if its trajectory brought it near the ecliptic plane where Earth and other planets orbit, if its magnetic field orientation happened to align unfavorably with the interplanetary magnetic field, then perturbations might propagate farther than normally expected. The heliosphere isn't static. It's a dynamic, magnetically connected system where disturbances in one region can affect others through field-aligned currents and wave propagation. 3I Atlas passed relatively close to Earth's orbital path, within roughly 50 million kilometers, which is close in heliospheric terms, though not in direct interaction range. Its perihelion occurred in late November, and it crossed Earth's orbital distance outbound in early January. If the object disturbed local plasma conditions, those disturbances would propagate outward at the solar wind speed, roughly 400 to 700 kilometers per second depending on current conditions. A disturbance created in late November would reach Earth's location by late December or early January. The mechanics of how an interstellar object might influence the heliosphere deserve closer examination. When 3I Atlas moved through the inner solar system, it wasn't traveling through empty space. The region between planets is filled with solar wind, a continuous stream of charged particles flowing outward from the sun at supersonic speeds. This plasma is magnetized, carrying frozen-in magnetic field lines that connect back to the sun's surface. Any object moving through this environment must push the plasma aside, creating a disturbance analogous to a boat moving through water. For most solar system objects, comets and asteroids on ordinary orbits, this interaction is well understood and relatively benign. But interstellar objects are different. They arrive with velocities that can exceed 50 kilometers per second relative to the sun, significantly faster than typical cometary speeds. This higher velocity means the bow shock they create is more pronounced, the wake they leave is more turbulent, and the magnetic field distortions they generate are more complex. The magnetic field carried by 3I Atlas itself represents an unknown variable. Interstellar objects spend millions of years exposed to galactic cosmic rays and the weak magnetic fields of interstellar space. Their surface ices can become magnetized. Their internal structure, if they contain metallic components or conductive minerals, can carry remanent magnetization. When this unknown magnetic field configuration encounters the Sun's magnetic field, the interaction isn't necessarily smooth. Magnetic reconnection events could occur at the interface. Field lines could become tangled, creating topological complexity that propagates downstream. Does any of this matter? Probably not. The energy involved in plasma disturbances from a kilometer-scale object is minuscule compared to solar wind variations from coronal holes. Mainstream space physics doesn't consider interstellar objects as relevant factors in space weather. The Sun outputs roughly 10 to the 26th watts continuously. A single coronal hole can accelerate solar wind to speeds that carry energy fluxes dwarfing anything a small comet could contribute. By conventional analysis, 3I Atlas should be irrelevant. But what if we're not asking the right question? What if the issue isn't whether 3I Atlas caused disturbances, but whether its passage coincided with existing instabilities in ways that amplified effects we're attributing solely to solar activity? Complex systems exhibit behaviors where small inputs can have disproportionate outputs when the system is already near a transition point. The solar wind approaching Earth this weekend originates from a coronal hole. That's clear. But the interplanetary medium it travels through was recently traversed by an object carrying an unknown magnetic field configuration and potentially creating plasma density variations. Whether those variations still exist, whether they interact with the solar wind stream, whether they alter the coupling efficiency when the wind reaches Earth's magnetosphere, none of this has been modeled because we don't track interstellar objects as space weather variables. Our space weather forecasting focuses on solar sources, coronal holes, solar flares, coronal mass ejections. We monitor the solar wind at the lone Lagrange point, 1.5 million kilometers upstream from Earth, giving us roughly 1 hour of warning before disturbances arrive. But we don't account for modifications the solar wind might have experienced passing through regions disturbed by interstellar visitors. The analogy might be weather forecasting that predicts a storm based on atmospheric conditions but doesn't account for the terrain the storm crosses. A hurricane gains or loses strength depending on whether it travels over warm ocean water or cool land. Similarly, solar wind traveling through pristine heliosphere behaves differently than solar wind passing through regions with residual turbulence, altered plasma density, or magnetic field complications left by a recently departed object. The timing is what generates curiosity rather than certainty. An interstellar visitor passes through during solar maximum, near Earth's orbital path, and exits the inner solar system, just as a significant coronal hole rotates into Earth-facing position. Is that coincidence? Almost certainly. But almost isn't the same as certainly. Unknown unknowns in space physics remain plentiful. We've studied the Sun and solar wind for decades, but we've only encountered 3 confirmed interstellar objects. Our understanding of how they interact with the heliosphere is based on theoretical models, not comprehensive observations. Consider also the psychological dimension of encountering interstellar objects. 1I/Oumuamua sparked intense debate about its nature, with some researchers suggesting non-natural origins based on its unusual acceleration pattern. 2I/Borisov appeared more conventionally cometary, reducing some of the speculation. 3I Atlas falls somewhere between exhibiting expected cometary behavior while maintaining the mystique of interstellar origin. Each encounter reminds us how little we know about what travels through the galaxy, what might pass through our solar system undetected, and what effects these visitors might have on the local space environment. 3I Atlas is gone now, accelerating into the darkness between stars. It won't return. Whatever effects it may or may not have introduced into the inner solar system are behind us. But it passed through at the same time. Everything else started converging. The solar wind acceleration, the Schumann resonance anomalies, the Oarfish sighting, the seismic gap tension. Maybe it's irrelevant, maybe it's a footnote, or maybe we're missing connections, because we haven't learned to look for them yet. The broader implication isn't about 3I Atlas specifically, It's about our incomplete inventory of factors influencing Earth's space environment. We know the major players: the Sun, the solar wind, Earth's magnetic field, the ionosphere. We understand the primary interactions, but rare events, interstellar visitors, unusual solar wind structures, magnetic field configurations that occur only during specific combinations of conditions, these remain poorly characterized. When multiple rare events overlap temporally, we lack the comprehensive models needed to assess whether their interaction creates emergent effects beyond what each would produce individually. Maybe the question isn't what caused this, but why so many systems are near threshold at once. Why an interstellar object, solar maximum activity, electromagnetic anomalies, biological signals, and tectonic stress indicators all converge in the first week of January 2025. Coincidence remains the most likely explanation, but coincidence doesn't preclude consequence. Sometimes unrelated factors align accidentally and nothing happens. Sometimes they align and the convergence itself becomes significant, not because any single factor was sufficient, but because their combination created conditions that individually none could produce. Asking when California's major earthquake will occur is the wrong question. Seismologists cannot predict earthquakes. No reliable precursor exists that allows forecasting a specific event with certainty. The physics of fault rupture involves chaotic processes, microscale interactions between rock surfaces, pore fluid dynamics, and stress concentrations that vary over centimeters in ways we cannot measure. Earthquake prediction remains firmly outside our capabilities, and likely will remain so. But prediction isn't the only form of useful knowledge. Understanding convergence, recognizing when multiple systems approach threshold states simultaneously, provides a different kind of insight. It doesn't tell us what will happen or when. It tells us we're in a period where the probability distribution has shifted. Background conditions have changed. What would normally be ignorable perturbations might now matter. Complex systems don't distribute events evenly over time. Earthquakes, solar storms, volcanic eruptions, financial crashes, all exhibit clustering. Periods of quiescence, where little happens, alternate with periods where multiple events occur in rapid succession. This isn't because events cause each other directly. It's because the underlying conditions driving all these events vary over time. When those conditions align, when multiple drivers reach peak values simultaneously, the probability of rare events increases across the board. Earth's tectonic system and the Sun's magnetic cycle operate on different timescales and are governed by different physics. There's no reason they should synchronize, except that they're not entirely independent. The Sun's magnetic field extends throughout the solar system, coupling weakly to planetary magnetic fields. Earth's magnetic field extends into space, responding to solar wind pressure. The ionosphere mediates between space, environment, and atmosphere. The atmosphere couples to the crust through pressure loading. The crust contains faults that are loaded by tectonic forces and modulated by everything else. These couplings are weak. Under most conditions, they don't matter. A geomagnetic storm occurs, some auroras appear, power grid operators watch for induced currents, and life continues. A coronal hole faces Earth. Solar wind speed increases. Satellite operators adjust orbits, and nothing dramatic happens. An earthquake happens in California. Buildings shake, the fault releases stress, and space weather continues indifferently. The systems are loosely coupled, influencing each other only at the margins. But margins matter when systems are near thresholds. A fault at 50% of failure stress doesn't care about a geomagnetic storm. A fault at 99% of failure stress might. The metastable boulder on the ridge doesn't move when wind blows. But when it's balanced perfectly, and the wind arrives at the same moment as rain loosens the soil and a small animal brushes against it, the coincidence of factors becomes significant. We don't know if California's faults are at 99% loading. We can't measure in situ stress on faults directly. We infer stress from GPS measurements, from earthquake statistics, from laboratory experiments on rock mechanics. The models suggest late cycle loading. The seismic gap suggests accumulated strain. The surrounding region's earthquake history suggests stress transfer. But quantifying exactly how close to failure any specific fault segment is remains impossible with current technology. What we can recognize is pattern. Multiple weak signals appearing together. Electromagnetic anomalies in the Schumann resonances. Biological behavior changes in deep-sea organisms. Solar activity delivering sustained pressure to the magnetosphere. Tectonic stress indicators showing elevated activity around a locked fault segment. An interstellar object passing through during the same time frame. Individually, none of these constitute evidence of imminent seismic rupture. Together, they suggest we're in a window where conditions differ from background. Science explains tendencies, not schedules. Probability distributions, not certainties. We can say that during periods of high solar wind speed, geomagnetic activity increases. We can say that geomagnetic activity drives telluric currents in conductive crust. We can say that California's major faults are late in their seismic cycles. We can say that late cycle faults become more sensitive to perturbations. But connecting these statements into a predictive chain requires certainty about coupling mechanisms that we don't possess. The appropriate response isn't panic, it's preparedness. California's seismic hazard is constant. The state exists on an active plate boundary. Large earthquakes will occur. The timing is uncertain, but the inevitability is not. Whether they happen this week or next year or a decade from now doesn't change the fundamental requirement for earthquake-resistant infrastructure, emergency response planning, and public education about seismic risk. What convergence thinking adds isn't prediction, it's context. It identifies periods where background conditions shift, where multiple systems align, where the probability landscape temporarily changes. During such periods, attention becomes warranted. Not because catastrophe is certain, but because the conditions that enable catastrophe are present. Weak signals that would normally be dismissed as noise become worth monitoring. Anomalies that would individually mean nothing gain significance through their temporal clustering. The high-speed solar wind from the coronal hole will arrive this weekend. It will compress Earth's magnetosphere. It will alter ionospheric currents. It will drive telluric currents through California's crust. Whether this influences fault behavior depends on questions we cannot yet answer. The stress state on specific fault segments, the current pore pressure in fault zone fluids, the microscale asperity distribution on fault surfaces, the exact coupling efficiency between magnetic field variations and crustal conductivity, all unknown, all potentially relevant. Are we still early in the window or already inside it? The honest answer is, we don't know. The convergence is occurring now. The solar wind arrives in days. The seismic gap remains locked. The biological signals appeared. The electromagnetic anomalies were recorded before monitoring went dark. These are facts, observations, measurements. What they mean for earthquake probability over the next week or month remains speculation built on incomplete understanding of coupled Earth systems. Civilization plans for averages. We build infrastructure to withstand typical earthquakes, not maximum credible events. We forecast space weather based on historical patterns, not worst-case scenarios. We design systems to handle expected loads, not convergent extremes. This works until it doesn't. Until multiple rare events align. Until the systems we thought were independent turn out to be coupled just enough to matter. The convergence is observable. Whether it's meaningful depends on what happens next. Either the solar wind arrives, the magnetosphere compresses, telluric currents flow, and California's faults remain locked because the perturbation isn't sufficient to overcome static friction, or something different happens. A moderate earthquake releases some stress. A major earthquake ruptures a locked segment. A sequence of events begins that will retrospectively identify as having been triggered by the convergence of factors we're discussing now. If nothing happens, the signals we've observed will be filed as interesting anomalies, data points in the ongoing effort to understand Earth system coupling. If something does happen, every signal will be reanalyzed for its potential predictive value, and we'll face the same challenge we always do. Pattern recognition after the fact proves nothing about causation. Convergence thinking doesn't enable prediction. It enables recognition that we're in a state space, different from background. And sometimes, that's all the warning we get. Are we still early in the window or already inside it?